morning. So we're going to start today with Ben. He's going to speak about his Pathset framework for lower bounds.
All right. So, so this talk will be about lower bounds for formulas. So in general, I'll be talking about DeMorgan formulas, so and or not formulas, and special subclasses, so AC0 and monotone cases. So, okay, as we all know, proving superpolynomial formula size lower bound for explicit function is one of the major frontiers in complexity. So the strongest lower bounds we know currently are almost cubic. So the class of languages computable by polynomial size formulas is known as NC1. So it sits here in this hierarchy of classes. So we have our small classes here, maybe what you could call medium classes, and our large classes. So the question is, where should we be looking for lower bounds? If our goal is to prove a superpolynomial formula size lower bound, what kind of problem should we focus on? Well, one very natural approach is to first try to prove lower bounds for the very hardest problems. So, and I guess recently there's been success in this mode, starting with this line of work of Ryan, separating ACC0 from NX. But if we look at some of the classic era lower bounds for these very small classes, what we can observe is that their lower bounds, typically average case lower bounds, for what you could call the easiest hard problem. So, the techniques we have for AC0 lower bounds naturally apply to the parity function, which would lie here, and even the nearly cubic formula size lower bounds are for Andreev's function, which in fact has a cubic formula size. And I think when we're looking at average case techniques and the probabilistic method, there's a good reason for this. We want to have some handle on the problem, and naturally, problems with lower complexity we could expect to develop techniques to say something about. So if our goal is lower bounds for NC1, we want to look for the easiest hard problem that is outside of that class. And so I'll propose that the average case k-cycle problem, or equivalently the distance k ST connectivity problem, would be a good candidate for the easiest hard problem that's outside of NC1. Okay, and so throughout this talk, you can think of k as being some large constant or some barely super constant function. So let me talk a bit about this average case k-cycle problem. So I'll be considering a version of the problem on layered graphs. So here I have the k-cycle graph. Okay, so I'm identifying the two endpoints here. And we're going to be considering as inputs graphs on kn vertices arranged into layers, and we have edges in between consecutive layers. And the question is there a k-cycle going across like this that starts and ends at the same vertex? Okay? So this is the k-cycle problem. And this is equivalent to, well, it's almost identical to the iterated Boolean matrix multiplication problem. It's also equivalent to this distance k ST connectivity problem. So in the average case version of the problem, we'll be considering an input which is a random layered graph with independent edge probabilities that are chosen around 1 over n. Okay, so we can fix this edge probability so that the probability of a k-cycle is exactly 1/2, let's say. So this is like a layered Erdős-Rényi graph. Okay, and this is about the simplest kind of random graph. Well, it's quite a simple random graph. It has constant average degree, for example. And an alternative distribution which the same intuitions hold would be k random permutations. Everything I'll say would apply to either of these distributions except for the lower bounds in the monotone settings where we'd have a difference. So to understand this problem in the average case version, let me first go through the upper bounds for this problem. And here there's a difference I want to point out between the worst case and average case versions. So the formula size, in the average case, we actually get something a little better. I'll explain why. And when I claim the average case version is in deterministic log space, so we actually have, because this is constant average degree, we can do it simply in log space, whereas we'd have an NL upper bound in the worst case setting. And moreover, you can implement these upper bounds by monotone AC0 formulas. And this upper bound could be implemented by monotone switching networks of just polynomial size. So the Pathset framework that I'll try to say something about is giving a lower bound for the average case K-cycle problem for both AC0 formulas and also for unbounded depth monotone formulas in the regime of small k. And to mention, so in the worst case setting, for different monotone models, we know lower bounds of this form for monotone formulas in the classic work of Karchmer and Witkerson, and very nice work of Potetchin giving these bounds for monotone switching networks, and the recent work of Robert for monotone span programs. We have lower bounds for the worst case complexity. And to point out, these two lower bounds simply couldn't apply for the average case version of the problem, since it has polynomial sized monotone switching networks. Okay, and the ambitious goal of this line of research would be to extend the framework to get lower bounds for general DeMorgan formulas. Okay, so so let's build some intuition by first looking at the upper bounds. So the classic upper bound giving the best formulas for this problem would be the recursive-doubling algorithm. The idea is we're actually going to compute the set of all, we want to determine whether there's a path between every pair from the left and the right. And to do this recursively, you would find all the information of whether there's path between every vertex on the left and in the middle. Similarly for the middle to the right. And then you merge the result of these subcomputations. So this is computing a Boolean matrix product. Okay? And if you if you implement this by formulas, you would get something which is n to the log k size, solving this k cycle, in fact, on all instances. So this would be a worst case algorithm, right? So this is also the idea behind Satvich's NL algorithm. Okay, good. So we can actually do something better in the average case. And I'm going to present this as a way of introducing and motivating path sets. So to recall, we're looking at a random layered graph with independent edge probability around 1 over n. And let me call this gamma, just to refer to this random graph. The random input, it will be gamma. Okay, and here's the idea. So if we look at any square root n vertices on the left and any square root n vertices on the right, then on average, gamma would contain just constant many paths which start here and end here, okay, with very high probability. So the idea is, imagine we have formulas. We're going to look at the left half here and root n vertices here, root n vertices here, and okay, on average, there's just constant many paths. And imagine we have formulas which are spitting out the value of this path. So we have maybe order log n formulas whose output simply explicitly says what these paths are. And if we do this also for the right here, then we can merge the results of these subcomputations to see whether the constant many paths here line up correctly with the paths here to form a path going all the way across. Okay, and if we, most of the time this won't happen. If we look at log n blocks of log n vertices in the middle, then we'd expect to see one path going all the way across through one of these.
Sorry, the block in the middle is log n or root n?
Oh, I'm sorry, root n. If I said log n, I mean root n. Yeah, thank you. Right, root n. Okay. Okay, so this. Right, so if you implement the formulas this way, you'd get root n to the log k size formulas for the average case version of the problem. Okay, so this is where we get something better in the average case. Okay, so right, I want to use this average case algorithm to motivate path sets and what I'll call Pathset formulas. Okay, and you can think of these as maybe a class of algorithms which operate on a similar principle to this one. So a path set so we're going to be considering a subgraph of the K cycle. Okay, so denoted by G. And then a G path set is going to be a set P of embeddings of G. Okay, so by which I mean an embedding of G, you just map each vertex of G to one of the vertices in the cloud below it. This describes an embedding of G down below here. So P is a set of those. And we're not going to be considering all sets, but only sets which are small in some sense, so subject to some density constraints. And these density constraints are going to guarantee that for this random graph gamma, that it contains just constant many, gamma contains constant many of these embeddings with high probability. Okay?
So
this is the
this P is fixed in advance before gamma is chosen.
yes, P is fixed in advance. Yeah, right.
Do you want at most a constant, at least a constant, or both?
At most a constant, and not only an expectation, but this is going to ensure that the probability that gamma contains, say, n to the epsilon elements is going to be exponentially small. This is what the definition is going to guarantee. So let me just say what are the density constraints. I should say these definitions aren't right. It's not terribly important what the exact definitions are, just to give you, but it's easy enough to state. So so if G is just a path, we simply require that the density is at most 1 over n. So for example, if we have all paths like this that start and end in some fixed set of root n vertices, this has density 1 over n. Another example, which would be a non-rectangular path set, would be I could take all embeddings like A, B, C, where the sum of them is congruent to 0 mod n. So if your G has is the disjoint union of 2 paths, then we get 3 density constraints. So we require that the overall density is at most 1 over n squared, and we require that for every way you could fix this embedding x1, then the conditional density over here would be at most 1 over n, and similarly if you fix x2.
Then can you, what is the definition of density?
Density would be just the fraction of embeddings which are in P. So in this case, it would just be the size of P over n cubed. Okay. Right. Okay, and finally, in the case where G is the entire k-cycle, there's no density constraints. So in particular, we have the complete k-cycle path set, so the set of all k-cycles. Okay? And this is going to be the object that we're trying to build in this path set framework. Okay, and so we're going to be looking at ways of constructing path sets, and we have 2 operations. We can form a union of 2 path sets, so long as the union satisfies the required density constraints. And the other operation is a join operation. If I have a G path set P and an H path set Q, the join is a G union H path set. This is the definition, but just as a picture, for every element of P and element of Q, which coincide on the common vertices, then the union of those 2 paths would be an element of the join. Okay. So we have these 2 operations, and if you want to think of these path sets algorithmically, so if I have an algorithm which is given gamma tells you the elements of P that are in gamma, and similarly I have an algorithm which given gamma says the elements of Q which are in gamma, then we could form one for the join. Since they're just constant many, you just sort of merge the results.
When you say whenever density constraints are satisfied, you mean on the union?
On the union.
And also on the join.
The join, it's automatic actually, but yes.
So, yeah.
It's typically empty, the join? The join is typically empty, like in...
Typically empty?
typical, if...
Depends on P.
Yeah. So you should think of join as a hybrid of the product and the intersections. If G and H are disjoint, this is the product. If G equals H, this is the intersection. Yeah. But yeah.
Stupid question. I think you said it, but so are we trying to construct these pathsets?
Yeah. Right. So we're trying to construct it. So let me say a bit more about it.
They will sort of like witness the lower bound in some sense.
Yeah. Think of this as the upper bound. As the type of, we're going to think of this constructions of paths as a certain type of formula that we want to prove a lower bound for, right? So a Pathset formula will be, this is a bit informal definition, but so we'll think of a formula where the inputs or the leaves are labeled by the atomic path sets. So where G is a single edge and P is a single, is a singleton. And then we have union and join gates, again, subject to these density constraints. So, maybe all the elements of this formula are typed by some subgraph of the K-cycle, and then you have these kind of gates. So the objective, what we're trying to compute with these Pathset formulas, is to construct the complete K-cycle Pathset. So the set of all K-cycles or some dense subset of that. Yeah.
Can you go back to the previous slide?
Yeah.
So we should think of this as really the OR and AND gates in the formula, and you are applying the approximation method to the OR gates in throwing away the two dense things?
No, it's actually different. Yeah.
What are my atomic Pathsets again?
Just when G and P are singletons. Yeah. So I don't want to get too caught up in definition, but I just want to give a sense. The takeaway should be this is some model of computing objects which are in some sense simpler than Boolean functions, and also correspond in some sense to average case algorithms. So this average case recursive doubling algorithm that I showed is giving an n to the 1/2 log k upper bound on the Pathset formula size of the complete K-cycle Pathset. But in the setting, there are actually other sort of surprising algorithms that are also reasonably efficient. So if all of your joins are of graphs G and H of this form, which overlap like this, you can actually get a an upper bound of the form n to the natural log of k, sort of surprisingly. So, and so the main lower bound here for this Pathset formulas is that Pathset formulas computing a dense K-cycle Pathset require size n to the some constant times log k. Yeah.
Are these any sort of Pathset formula or constant depth?
These are this is unbounded depth. Yeah. Right. So so a lot goes into this lower bound. I mean, I hope I can say something about it. But so the idea of this Pathset technique is to reduce AC0 and monotone formulas and hopefully other kinds of formulas to this lower bound. So to say this again, if phi is a formula which is either AC0 or monotone, and let's assume it solves the average case K-cycle problem, the idea of the technique is to convert phi to a Pathset formula which is computing a dense K-cycle Pathset. And then we can appeal to this lower bound on the last slide to get our lower bound of n to the omega log k. So this is the high level. Right, so I'm going to, in just 2 minutes, go through and just sort of illustrate what I mean by this in the case where phi is both AC0 and monotone. In fact, let me even skip the definition of what this is. So here we have some formula. And the idea is we want to, for every gate in this formula and every subgraph of the K-cycle G, we want to consider some Pathset, some G Pathset associated. So what this is it's the set of, this is the set of minterms of this shape. Okay? So just so you can see how this relates to this notion of Pathset formulas. So at the ors of the formula, we can see the minterms of an or, the G-shaped minterms of F or G is contained in the union here. In the case of, I thought I had an and. I left out the and slide. So for the and, you get something in terms of union of joins. And then at the inputs, you have either empty or atomic Pathsets. And to get a lower bound for monotone AC0 formulas, it would be enough to consider the random graph here and to view this as a restriction. So apply this monotone restriction to all gates in the formula. So I'll denote that by this F union gamma. And then you have these relations also hold under the restriction. So just the takeaway here is that, we have a bunch of these Pathsets, and we can see somehow that they're being constructed by unions and joins. And then the key lemma which one could show in the case where this formula was a monotone AC0 formula, you could show that under this random restriction gamma, all of these sets would in fact be Pathsets. So it would satisfy these density constraints with extremely high probabilities. You could take a union bound. Okay, so this is sort of impressionistic, but just to show you how, so you can see how a Boolean formula induces a Pathset formula. Right, and then finally, if you assume that this formula solves the average case K-cycle problem, then if you're looking at the sort of top pathset here, so this K-cycle pathset at the output under a restriction, then this would be computing a dense K-cycle pathset with some constant probability. So this lets us appeal to the lower bound. So this is very hand wavy, but just to show you how the technique looks like.
In particular, what this shows is that in monotone or AC0 formulas, every gate has a shape after the restriction.
No, so there's there are a lot of complications because we have for every gate, we don't associate it with a single type. We have for every graph G, we get a path set. Somehow out of that, you have to extract a shape. Maybe I'll say something about it in a bit. Right, so the idea is that, so sort of generalizing the results we have in both the AC0 and monotone settings, so we can sort of apply this Pathset lower bound to a DeMorgan formula whenever all subformulas have low G subgraph sensitivity in some sense, okay, at a random gamma. So, if our formula is merely AC0 or monotone, then we require a different way of defining these pathsets. We're not just looking at min terms, we're looking at more complicated definition here. But the hope is that for general DeMorgan formulas that, certainly I think what's needed here is sort of a top-down definition of these pathsets. So in these cases, you can define the pathsets just in terms of the Boolean function here, but maybe one needs a top-down definition to get for any hope of this working for general DeMorgan formulas. Let me not say, right, so what I mean by low G subgraph sensitivity is going to be a bit hazy here, but just to say something in the monotone setting, we have our random gamma, and we want to say, is it sort of sensitive at this particular embedding? And in the monotone lower bound, we're looking at sort of adding random noise, which consists of some less than root n random paths. And somehow the key point here is that this random noise lives inside if you add this random noise to gamma, then the total variation distance doesn't change much, and that's how we're able to get average case lower bounds. So yeah, let me briefly say something about how this Pathset formula lower bound is proved. So this is the lower bound for Pathset formulas, and right. So the key to proving this lower bound is to look at a sort of a form of Pathset formulas where we restrict the type of joins, or we fix the pattern of joins. So what I'll call a join tree is just a binary tree where the leaves are labeled by the leaves are labeled by the edges of the K-cycle, and every edge appearing at least once. So this would be the recursive doubling pattern here, okay? So we construct each segment here as a union like this. And with respect to these join trees, we get this n to the 1/2 log k upper bound. So this maximally overlapping join tree, which I mentioned before, this gives a construction of n to the natural log k upper bound.
How do you see the complexity from the formula?
What's that?
How do you see the complexity from the tree?
Right. I'll say something in a minute. And you could also look at very skewed join trees like this. And in some sense, this is going to correspond to constant depth formulas for very small depths, for depths below k. And so something which I was able to show recently is if you have join, right, so okay, using some generalization of these patterns, you can get sort of the optimal tight upper bounds for the upper bounds for AC0 formulas with depth 2D you can witness with join trees of this form. Okay, so the way that we bound Pathset formula size is via this notion of Pathset complexity with respect to fixed join trees. All right, don't worry about understanding the definition. Just the point is, so this is some complexity measure with respect to any join tree over a subgraph of the K-cycle and any pathset over that graph. And you can define it as a pointwise maximal function satisfying certain inequalities. What I want to highlight here is that this is subadditive with respect to unions, but we just take the maximum with respect to joins. And so the sort of main lower bound, what everything boils down to, is proving a lower bound for every join tree for the k-cycle. We prove a lower bound on the pathset complexity with respect to that join tree in terms of the density of P. Right, I wanted to point out that so in the original paper, this constant here was 1/6. And yeah, an anonymous referee sort of tightened the analysis and improved this constant. I was very impressed. I don't know who you are, but if you're in the audience, I wanted to take this opportunity to thank you. Yeah. Okay, and just to mention, so there are many special cases of this lower bound which make the problem much easier than the general case. So one example being if alphas read once, so each edge of the k-cycle appears only once as a leaf, you can actually prove a completely tight lower bound using essentially just Cauchy-Schwarz. So something which I showed recently was if your alpha has left depth d, okay, which is less than log k, so every branch in the join tree goes left at most d times, then you get this improved lower bound. Okay. I was going to say I'm going to skip this part, but I was going to say where this comes from. It's some interesting, purely combinatorial problem about join trees. Right. I'm just going to skip this in the interest of time, so I can mention some next steps in this line of research. Right. So, as I said, the goal is to try to apply this technique more generally to DeMorgan formulas. But there's even in the AC0 and monotone settings, there's some ways that the technique I feel should be sharpened before one attempts to generalize it further. So, right. So one thing so we have this lower bound for bounded depth patterns here, okay, in the pathset complexity world, but I don't yet know how to get to translate this to a lower bound for AC0 formulas with very small depth, okay? So proving this would be sharpening, giving a tight version of this pathset trade-off for AC0 circuits for the worst case version of the k-cycle problem due to Shi-Chen, Igor, Rocco, and Liang. And just to point out, so we have this lower bound of n to the omega log k. This holds up to very large depths, okay? So unbounded in k, up to nearly log n. So this is something which one should be able to get out of the technique when the depth is very small. Okay, so here to highlight so there's an asymmetry in the definition of the pathset complexity. For OR gates, this is additive. For AND gates, we have a maximum here. And this suggests that we should be able to prove asymmetric lower bounds for monotone formulas.
What does it mean, high alpha beta?
Okay, yeah. So this is the join tree, which has alpha on this side and beta on this side. Yeah. If you look at the worst case monotone formula lower bounds for k-cycle, Karchmer and Whitkerson, they naturally are asymmetric. If you want to think of the KW games, it says that either the player holding the k-cycle has to communicate log k log n bits, or the other player has to communicate n to the epsilon bits. And I think one should be able to show the same thing in the average case setting, say for monotone formulas. Even for AC0 formulas, I believe this should be true. And I think the Pathset technique should be able to show this, but somehow, this corresponds between AND and OR gates, and the Boolean formula is not exact. So it's right. Another natural next step would be to try to apply this technique to other classes. So to AC0 formulas with parity gates. Another setting would be to multilinear arithmetic formulas computing the iterated matrix multiplication. So this arithmetic algebraic version of the k-cycle problem. Here recently, so there are some nice lower bounds of Shrikant and others in the case where n equals 2, and also in the bounded depth setting, but this is maybe another good case. And I believe also because of the asymmetric nature of ANDs and ORs that the Pathset should be giving a lower bound for monotone comparator circuits, but this is also another challenge. So also would be interesting to improve this to the optimal constant, say. But maybe more generally, So one can view this as this lower bound as in the form n to some parameter depending only on the k-cycle. And one can even generalize this, this whole approach from the k-cycle to arbitrary kind of fixed pattern graph H and ask about the formula complexity of average case H subgraph isomorphism. And right, if you want to view this as a sort of lifting theorem from some parameter of the graph H. So in some recent work with Kenichi Korabayashi, we tied this parameter to tree width polynomially, but sorry, tree depth. Right, it would be interesting to understand this graph parameter better. And then the final thing I wanted to mention is, so this whole technique is really quite narrowly tailored to this average case k-cycle problem. So one of the results is that average case k-cycle problem is hard for monotone NC1. It's not in monotone NC1. I don't know how to apply this technique to show that even the k-click problem is in the average case is not in monotone NC1. Somehow the average case distributions for k-cycle are much simpler. We can say things about these that I don't know how to say about just GNP for k-clicks. Right. Okay, thanks.
So maybe you have a little more time to explain. Every gate in the circuit in the reduction flow, let's say from monotone or from AC0 to the Pathset formula,
Yeah.
will it be eventually associated with one type or many types? Because the low bound of Pathsets that you have shown are for
Yeah.
types.
Yeah, so right. Okay, so here's just the simplest case of when the form is both monotone and AC0, then we only have to look at these minterms. And for ORs, we have no problem in some sense. So the complexity here is in these AND gates. All you can say is that every minterm of F and G is the union of a minterm of F and the union of a minterm of G. So we get an expression like this. We have to take the union over all ways that G can be formed as the union of two sets, and then we're taking the joins of these relations. This is the most.
So every gate is really associated with a collection of types.
Yeah, collection. And then to get the lower bound in terms of join trees, what one does is you look at the top. You have this dense path set at the top, and you want to look at how each minterm there was constructed, and that gives a sort of join tree. You can sort of partition that set into join trees. So when I said that all these techniques work for small k, we're paying a factor of 2 to the 2 to the k in the lower bound. So that factor of 2 to the 2 to the k comes out of the density at the top, because we're just picking we're looking at the most frequent join tree, and then we really exploit the structure of these join trees in the lower bound. So this Pathset complexity measure, I entirely skipped. So the combinatorial main theorem is this lower bound. I've never had time to say any kind of details about this, but you really study this Pathset complexity measure in terms of join trees, and you show that it has some nice properties. It's monotone under notion of projections onto subjoin trees, and there's a notion of there's another operation on. Right. Okay. So there's things you say, structural things you show about this that allows you to prove this.
Well, if I summarize your long answer is that you take the general, let's say, monotone circuit, you get from it a Pathset formula, you get from it a Pathset formula, and then you take only the most popular joint tree out of that and apply the lower bound. You have this.
Yeah, that's right.
Progress measure to it, and that's it. And
that's
you know
right.
something which is small enough.
Right.
So this is a monotone, because the Pathset complexity is a monotone measure.
Yeah, it is. Yeah. It is. Yeah. All right. Well, thanks again.